All right, Chapter 5, Thermal Energy, Section 3, Using Thermal Energy. Let's just go up here and review real quick. Temperature and thermal energy. Remember, heat, temperature, thermal energy. Temperature is just a measurement of the kinetic energy of the particles. And the kinetic theory of matter is huge. All matter is made up of tiny particles. Those tiny particles are in constant motion. At a higher temperature, the particles move faster. At a lower temperature, they move slower. At the same temperature, more massive particles move slower than less massive particles. Huge, huge, huge. So kinetic energy and temperature. The temperature of an object is the measurement of the average kinetic energy of the particles. All right. Then we had thermal energy. We talked about thermal energy. Thermal energy is the sum of the kinetic and potential energy of the particles. A lot of you missed that answer in the homework. Temperature and thermal energy. As temperature increases, thermal energy depends on that temperature. Mass and thermal energy. More mass, the more thermal energy, because the more particles there are. Heat. Heat always travels from hot to cold. Something hot always heats up something cold. If you were to touch this burner, you're going to burn your hand because your hand is cooler. Specific heat, a lot of you missed this in the homework. Also, compare water with specific heat. You guys put down, most of you said that was true, 1 degree Kelvin or 1 Kelvin. It's not. It's 1 degree Celsius. 1 kilogram of a material, 1 degree Celsius. All right, then we started talking about conduction, convection, and radiation, the way this heat or this thermal energy is transferred, okay? Conduction is when particles are touching, like putting your hands together and holding them together, or your hand, your rear end on the toilet seat, warming up the toilet seat. That's conduction. Two pieces of matter, two types of matter have to be touching for that transfer to take place. Thermal conductors have a high density. Then convection, it's the transfer of that heat or thermal energy by convection currents. And then finally, radiation. In the electromagnetic radiation is gravity. It's a long-range force. The electromagnetic force is a long-range force. And electromagnetic waves radiate out. And there's more than just the sun that radiates, and we'll talk about that coming up. Okay. All right. Thermal insulators, the particles are farther apart. Thermal conductors, the particles are close apart, or close. Conductors, particles are close. In insulator, the particles are farther apart. We explained how a double pane window works and how that keeps your house warm. And that brings us to using thermal energy. Now we know that heat or thermal energy transfers from hot to cold. And we know how that happens through conduction, convection, and radiation. Now we can use that energy. This tells us how we use that energy. So, different types of heating systems. All right, different types of heating systems. There is a forced air system. This is the most common and probably what you have in your house. Some sort of fuel is burned, and that fuel generates heat, and a fan blows through these ducts, and the heat is released into the rooms. Okay. It's a convection current. It heats up the air. The hot air rises and moves around. In some of the older homes, you may have what was originally gravity heat, or just a convection current in your house. And if you had that, you'll have a great big cold air return on the floor. It's just a vent, but it's huge. I have one in my house that's probably, 3 foot by 3 foot, maybe 3 foot by 4 foot. It's pretty big. And that's so the cool air can come back down originally to the gravity furnace, and it was heated, and then it went back out that way. But a forced air system and have some kind of a blower or a fan on it. That's what most of us have today. There are also radiator systems where the heat radiates out. Uh, in the notes, I'll have a good picture of some radiating heaters and how they work. All right. Then there are electric heating systems. Um, it doesn't have a furnace. Instead, there's coils and I skipped over radiating heaters, I guess, a little bit, but there are portable space heaters that are electric heating systems, and those are the most common. Radiator systems are like we have in the school, where hot is water is heated, and that heat, because of convection current, hot water rises. All of our heat in the school travels through the ceiling. As it cools off, it returns to the boilers in the janitor's room, is heated back up, and that steam and hot water again rises and passes through the school and heats up the school. Solar heating. There are passive and active solar heating systems. So in a passive system doesn't so much have solar collectors. It's just if you have a garage or if you have a building like the barn runs on a passive solar heating system. It heats up as the sun shines on it. There's no collectors or anything like that. And if you go in your garage, the doors have been shut, and you go in your garage in the summertime, it's pretty warm in there. All right. But that's passive. We're not trying to collect the heat. It just happens. All right. In an active solar heating system, we have some kind of a solar collector, and it transfers it says here radiant energy, but those electromagnetic waves from the sun into thermal energy. All right. And it collects it, and it can store it or circulate it through fluids when we're talking about a heating system. Probably not water, but some kind of a heating system. Could be water, but most of the time it's not. There's also down in the valley something that's called the geothermal heating system. And if you want to learn about that, you would have to take geology. That's where we would talk about that, would be in geology. All right, thermal dynamics. Thermal dynamics is the study of the relationship between thermal energy, heat, and work. All right, so work has to be done. Let me just jump down. Heat and work, an increase in thermal energy. Heat and work increases thermal energy. If you rub your hands together, all right, that is work. You are increasing the heat and the thermal energy. You can feel the heat build up between your hands. That's what it's talking about. For heat, if you need heat and thermal energy, you can do work on a system, all right? And here's the first law of thermodynamics, states that if the mechanical energy of a system is constant, the increase in thermal energy of that system equals the sum of the thermal energy transferred into that system and the work done on that system. And again, we'll look at it in the notes. I think it'll make more sense once we look at it in the notes. Here's the big one. The second law of thermodynamics basically says that heat travels from hot to cold. All right. The second law of thermodynamics states that the energy spontaneously spreads from regions of higher concentration, higher temperatures, to regions of lower concentrations or cooler temperatures. It's possible to do that backwards, but when we do that, we have to add energy. And when we do that, thermal energy into mechanical energy, we have to use what's called a heat engine, like a car, all right, a car system. And here's the process of how a car works, an internal combustion engine, all right? What kind of machines reverse the process and make cold go to hot instead of hot to cold? Refrigerators will do that. An air conditioner does that, and something called a heat pump. All right. It's a two-way air conditioner. A heat pump is a two-way air conditioner. So the process can be reversed, but for heat to flow or from cold to flow into warm objects, we have to have some kind of a heat mover or a heat engine. All right, so tune into the notes to get a little more information on it.